So, Akbar will be talking about three-body retarded dispersion potentials involving electric octopole coupling. So a complete change of gears here. You ready, Akbar?
Okay, good morning. I'd like to begin by thanking Hoban and the rest of the organisers for the very kind invitation to come and speak here. It's a real pleasure to be at this meeting and in Hong Kong. So as the title sort of says, I will sort of look at retarded dispersion interactions between atoms and molecules, and looking at the effect of electric octopole coupling in particular on three-body forces. So basically, we will employ the methods of molecular quantum electrodynamics to study these energy shifts involving three atoms or molecules. I'll briefly go over that. I think there are probably many experts in the audience who know molecular QED fairly well, as well as obviously the extension of the Casimir-Boulder potential to three bodies and many bodies, which we'll concentrate on. And so I'll sort of have this overall aim of my presentation today. Just to say that going beyond the Casimir-Boulder potential to look at their many-body effects, the leading contribution is the triple dipole dispersion potential. And so we'll look at that in a bit of detail, just sort of preempt the results that will follow involving electric octopole contributions. But that's not to say that the next highest order leading contribution beyond the electric dipole coupling term involving the electric quadrupole moment hasn't been looked at. Systematically gone through and looked at the corrections to the triple dipole dispersion potential. Those are in these publications here, but we'll just go from triple dipole to octopole coupling, and we'll see that the results that I get will hold for arbitrary arrangement of the three particles involved, and then we'll look at some specific geometries, equilateral triangle, collinear arrangement of the three species. So outline of the presentation will take this form here, just to give a brief motivation. In section 1, why looking at three-body interactions is important. Just a brief justification there, and then we'll dive into a very short overview of molecular QED theory, and then we'll, as I said, quickly look at the retarded triple dipole dispersion potential, how that interaction energy can be calculated really efficiently using great power form of coupling Hamiltonian, and then we'll look at the nature of the electric octopole coupling and see then how they come into play when we look at retarded dispersion potentials involving three atoms or molecules. So let's jump straight into the motivation part. So as I said, if we have a collection of n atoms or molecules that are interacting, they're coupled with each other, total interaction energy being E, and we subtract off then the sum of the single particle contributions, the one-center terms, then what remains then we'll call an energy shift, and that will then, by definition, be a sum of two-body contributions, the pairwise terms that contribute to the interaction energy, three-body terms, four-body terms, many-body contributions, etc. And these are genuine, non-pairwise additive three-body contribution to the energy shift, and we're looking at the dispersion potential, so dispersion energy, four-body terms, etc. So in an effort to improve the quality of global potential energy surfaces and get reliable and transferable intermolecular and interatomic potentials, especially in the ultra-cold community nowadays that are looking at collisions between atom-atom-atom to form dimers and trimers, similarly atom-diatom to form molecular trimers, as well as their dissociation pathways at ultra-cold temperatures and low energies involving alkali metals and group 2A elements, alkaline earth species. These now three-body contributions are becoming more important in terms of then getting accurate potential energy surfaces. Similarly then, noble gas elements in the gaseous state or in solid phase, looking at some of their thermophysical properties, for example, the third virial coefficient, which is very sensitive then to the intermolecular potential. These are then sort of justifications for looking at corrections then to the pairwise potential So that's sort of motivating the work looking at now extending our understanding of two-body interactions to now looking at contributions coming from genuine many-body terms. As I mentioned, we'll use molecular QED theory to calculate these energy shifts. And so we know that a fully covariant theory of QED exists, developed by Feynman, Schwinger, Tominaga, and important contributions by Dyson, as well as others, and led to this fully covariant formulation. But from the point of view of treating atoms and molecules, where the electrons, for the overwhelming majority of cases, are bound, they're moving with speeds a lot less than the speed of light, energy is a lot less than mc squared, we can use then a non-relativistic approximation, so this would be the non-relativistic limit of the fully covariant QED theory. That's usually called molecular QED or non-relativistic QED. It's formulated in the Coulomb gauge, where the divergence of the vector potential vanishes, so div A equals 0. But it can be constructed in its own right by starting off with the classical interaction for a charged particle with the electromagnetic field and carrying out the standard canonical quantization procedure through the calculus of variations, ending up then with the minimal coupling Hamiltonian. And that can be applied, and has been with a great deal of success in theoretical chemistry, chemical physics, atomic molecular and optical physics, condensed matter physics, etc. But there are other formulations of this molecular QED in terms of the multiple Hamiltonian, which has many advantages, as we'll see. And so both foundations of the theory, as well as applications to theoretical spectroscopy, nonlinear optics, scattering of light, as well as to interparticle interactions, energy transfer, for example, van der Waals dispersion, are in well-known texts and a recent review article, and many other papers and books cover this topic fairly well. So let's look at the multipolar form of the molecular QED Hamiltonian, basically in sum of three terms. A molecular Hamiltonian, so that's written here for a charged particle of mass m with momentum e. Then first term is then the kinetic energy, and then we have the intramolecular potential energy for charged particles alpha, which forms some atomic or molecular center. So it's familiar from ordinary molecular quantum mechanics. Second term is then the radiation Hamiltonian. That's an intrinsic part of the system, as we know in quantum electrodynamics, so it's ever present. Here I've written it in terms of microscopic transverse electric displacement field and magnetic field operators. So I've used SI units throughout, so that's where these other factors that come in front. But essentially the electric displacement field is given by this Fourier mode expansion here in terms of then the annihilation and creation operators A and A dagger, which then respectively decrease or increase the number of photons in the field by 1, or radiation of a particular mode, k lambda, where k is the wave vector and lambda is the index of polarization. And we have box normalization in volume V, and then this prefactor just ensures we get the correct energy for the field in vacuum, and a similar expression then for the microscopic magnetic field operator in terms of then the unit magnetic polarization vector, again linearly dependent on annihilation and creation operators. So the all-important coupling term now in the multipolar form is then given by this series expansion in terms of the electric polarization terms, the magnetization and the diamagnetization contributions. Here I'm written in terms of the electric dipole coupling to the electric displacement field, the quadrupole, the gradient of the electric displacement field, the octopole, two gradients with the electric displacement field. We'll concentrate on the mu dot d and the O coupling to the displacement field contribution in this talk. I won't look at quadrupole or magnetic dipole or diamagnetic contributions. So here are standard definitions for the various electric dipole, quadrupole, octopole moments for charge E alpha, position Q alpha with respect to some expansion point. Big R could be the origin center of inversion, center of mass, etc. So these are in their reducible form. And so we've got now matter coupling to radiation directly through the molecular multiple moments, coupling to the fields or through the gradients of the fields, rather than that minimal coupling prescription where we have P dot A of A squared and static interparticle interaction term. And now direct coupling between matter and radiation here, only one center contributions appearing in this coupling Hamiltonian. So how do we solve now this sort of equations for that Hamiltonian operator? We basically use perturbation theory, unsurprisingly. So we partition Hamiltonian into a part that we can solve. That's basically H mod plus H rad. So we're assuming that in the absence of radiation, our friends in the quantum chemistry community can generate accurate wave functions or densities using density functional theory, which we can then solve the eigenvalues and eigenstates and various molecular properties for that molecular Hamiltonian. Similarly then, in the absence of any sources of charge, we have a free radiation field, which we know the solutions to. So basically then that's a solved problem, we assume, and we take then that coupling Hamiltonian to be a perturbation on our system, and ask them the question, how does the system evolve in time under the influence of the perturbation as it makes a transition from initial state little I to final state little f, and expand in series of powers of perturbation, and then calculate the probability amplitude, from which we can calculate then observables, for example, the Fermi-Goldman transition rate, or the energy shift in terms of then the diagonal and off-diagonal contributions of the matrix element squared. And so we use an unperturbed radiation molecule product field states for our unperturbed states. So we'll use some quantum number or quantum numbers to then designate the appropriate states for our atomic and molecular system. We'll use a number state representation for the radiation field, although we're not restricted to that choice, obviously. Okay, so let's quickly go over then the triple dipole contribution to the retardant dispersion energy. Everyone, I think, is familiar with the Casimir-Boulder potential in this audience, so I think we can skip that and go straight to the three-body contribution. So we'll consider three neutral electric dipole polarizable atoms or molecules in their ground state, positioned at Ra, Rb, and Rc, species A, B, and C. So the total Hamiltonian then is going to be sum of three terms, one for species A, B, and C respectively. The radiation field is always there, and now we have three coupling terms, one for each species coupled to the field. We'll assume electric dipole in this first approximation, the leading contribution, and just like in the Casimir-Boulder potential, coupling occurs through the exchange of two virtual photons between each coupled species. So just as in the two-particle case, we have the same idea. So we will label these three virtual photons which are being exchanged between any two particles as 1, 2, and 3 for these different virtual photon modes. We'll label the intermediate states, virtual states that species A, B, and C can access from the ground state by X, Y, and Z respectively. And so if we're going to carry out this sixth order perturbation theory calculation using that form of coupling Hamiltonian linear in the electric displacement field, we would have to sum over 360 diagrams. It's obviously a lot of work. We might make mistakes. It's not easy to see how to sum the contributions. There should be energy denominators. So it's advantageous to then employ what's known as a Craig-Power Hamiltonian, where we have now, instead of the dipole coupling to the electric displacement field, we will couple the molecule by its electric dipole polarizability to the now the square of the electric displacement field. This can be obtained by canonical transformation and was done first by Craig and Power to calculate the Casimir-Boulder potential actually way back in 1969. So instead of now 360 diagrams, we have 6 diagrams of this type. We've got basically collapsed two-photon interaction vertices there. Each species still emits and absorbs 2 virtual photons, and all possible time orderings, as we know from Feynman's rules, to evaluate these diagrams. And so here's the standard definition for the electric dipole polarizability. And so for an arbitrary arrangement of the 3 species, A, B, and C, with these displacements, little a of d with respect to c, little b a with respect to c, and little c b with respect to a, and these internal angles, and then defining these direction cosines, we can then get an expression for the triple dipole dispersion potential, which comes out then in terms of the polarizabilities of imaginary frequency, omega equals ICU, of the polarizabilities of each atom or molecule. And so this is then the generalization of the Casimir-Boulder potential to the three-body case. And we can write this in terms of then this geometric tensor, Fij of UR, and compactly in this form. So this then holds for fixed orientation of the three species with respect to one another. So for then isotropic case, we need to then carry out an orientational average. And just to show you what that looks like, so for arbitrary arrangement of the three species, just the triple dipole comes out like that. So we can, just like in Casimir-Boulder potential, calculate the short and long range asymptotic limits. So in the near zone, we know that the particles are separated by distances a lot less than the reduced characteristic transition wavelengths of the downward transitions. And so we can make the usual approximation, just like we get the London dispersion from the Casimir-Boulder potential. We basically get then a form for this short-range triple dipole contribution, which is then known as the Axelrod-Teller-Mutter result, evaluated by them independently way back in 1943, and so has this then familiar geometric part and molecular part. Similarly, then in the far zone, we can do the same thing. Separation is now much larger than the characteristic reduced transition wavelengths. Basically, the polarizabilities are now static. They can be pulled out. We can calculate the U integral directly, and we end up with this form for the long-range asymptotic limit. So this holds for arbitrary separations at this point and any particular geometry. So let's then specialize specific geometries, and we'll choose an equilateral triangle first. And so obviously then the lengths are equal, the internal angles are equal, and we obtain then this form for the triple dipole potential. You may want to pay attention to these coefficients here. They will show up a little bit later. Similarly, interesting, too many equations maybe. Sorry about that. So we can calculate the asymptotic limits for the equilateral triangle case. We get then 1 over r to the minus 9 and 1 over r to the 10 for short and long range. Again, the retardation decreasing the strength of the potential by a factor of 1 over r. And we saw for the general case that the interaction potential was attractive, but here we're seeing now repulsive potentials, and it's quite well known that in the three-body case that the sign of the energy shift is dependent on the geometry that the three particles adopt. So we can also look at the collinear geometry, so we'll just basically bring C in between A and B, put it midway. So then so we have these displacements. So now theta A and theta B are equal to 0, theta C is 180 degrees, all three atoms line in one line. And then the general form for the triple dipole looks like that. And again, we get 1 over r to the 9, 1 over r to the 10, this time now attractive dispersion potential. And again, you may want to pay attention to these coefficients there. That's going to show up. So these near zone results agree with a calculation a long while ago using static electric multiple coupling terms by Bell in 1970. So let's look now at the contribution of the electric octopole moment. So we saw that the couplings of this form, so some octopole moment, ijk, and couples through two gradients in electric displacement fields. So we know that the displacement field vanishes for a neutral source outside where that source is situated. So that must mean then that when k equals I or j equals I, that the coupling vanishes, so that then places some restrictions on what the allowed components of the Octopod moment are going to contribute to the energy shift. And it's also convenient to now decompose this Octopod moment that I defined earlier into its individual contributions of weight 1 and weight 3. So here's the weight 1 term, basically transforms sort of like a vector and has selection rules similar to an electric dipole moment. And this has then 3 independent components, and then the usual third rank tensor, which has 7 independent components, 2 times 3 plus 1. And there's some useful identities relating these weight 1 and weight 3 contributions. So let's now calculate the contribution by replacing one of the species, particle C, which was electric dipole polarizable by one octopole moment. So now the coupling Hamiltonian in its Craig power form will take this particular expression here, where we define now the mixed dipole octopole polarizability in the usual way, which is going to be a sum of weight 1 and weight 3 contributions. And similarly then for future higher order terms, we want the pure octopole polarizable contribution as well. And so this is now the pure electric octopole polarizability, just analogous to the dipole one. And so this Craig power Hamiltonian then is of this form here. So now we're sort of ready to calculate various contributions coming from octopole moment to the specific three-body dispersion potential. So let's start off instead of just replacing one D with one O, put that in particle C, other two just as before. So we carry out the same type of calculation, nothing really different. We find that the oriented result has this form again, proportional polarizabilities of each species, and now the mixed dipole-octopole case. And we had that F tensor before, now there's another one that comes in that gives us the orientational dependence and angular dependence. So 2 additional gradients because we've got one octopole. So this is this complicated looking east over here, which will feature quite a lot. And we have to now do an orientational average for the isotropic case. And here now something interesting happens. Basically the weight 3 term vanishes, leaving only the weight 1 contribution for orientationally averaged potentials involving mixed electric dipole-octopole contributions. So if you remember the triple dipole case, it was FFF, but basically because now these two indices are the same, it's basically very similar to the F multiplied by this complex frequency square, so this seems to be implying then a higher order correction to the triple dipole potential coming from the weight 1 contribution of the octopole moment. For an equilateral triangle configuration, we get this form of potential, and so here we get the same coefficients that were showing up in the triple dipole case. Similarly then for the collinear geometry, we're doing for a set of coefficients. Note there's no UR independent term here, everything has a UR contained in it, so that means there's no near zone limit. These are fully retarded potentials, and because of that weight 1 contribution only, which only appears when the interactions are retarded, the weight 3 contribution comes in for retarded and static contributions. So in the far zone, we have an R-12 dependence, obviously very weak. So let's look at the next one now. Let's make atom B mixed electric dipole-octopole polarizable just like C. Do the same type of calculation, so only A is now dipole-dipole polarizable. Now we're getting 1F and 2L tensors. Oriented result looks like that. And again, the weight 3 contribution vanishes on averaging. And then for specific geometries, here we get now all the terms appearing that we had in the dipole-dipole-dipole case. Similarly then for the collinear geometry, so this is clearly a higher order correction now to the triple dipole potential. Again, there are no static UR independent terms in the general result or for any particular geometry. And we have then a far zone after -14, again very, very weak. We sort of get the picture now. We can look at the third case where we have now 3 mixed dipole-octopole polarizable, now proportional to the product of 3 L geometric tensors. On averaging again, the weight 3 contribution disappears, and we get then additional contributions corrections to the triple dipole potential for both general and specific geometries that were looked at are now very weak after -16 retarded correction. Let's look now, we've sort of put one octopole on each atom successively. Let's now look at the case where we go back to two of the species being dipole polarizable, A and B, but now let's make C purely electric octopole polarizable. The oriented result looks like that. Now, the weight 3 contribution doesn't disappear, it's still there after rotational averaging. This is now basically a sixth rank tensor, that polarizability. So the weight 1 and weight 3 terms survive, and the general result looks like this now, basically contributions from weight 1 and weight 3 both appearing. So now we have contribution which is then dependent on weight 1, which is a higher order correction for the equilateral triangle, plus now contribution which is dependent upon weight 3. So now there is a static UR independent term which will give us then a near zone limit. But the first term again has identical coefficients that we found in the triple dipole case. Not again. Sorry about that. Must be too many equations. First time I've given this talk. We fault with Microsoft Apple. And similarly then for the collinear case, for the DD-DD-OO, we'll get then a contribution dependent upon weight 1, which then has identical coefficients to the triple dipole case, but now a weight 3 dependent contribution, we will get then a static near zone limit as well as the usual far zone contribution, which will be the sum of both integrals. Here now we find an after -13 near zone and after -14 far zone potential. This is the last case that I'm looking at. Now we'll put 3 octopoles, but basically one purely electric dipole, one mixed, and one purely electric octopole. So then the coupling Hamiltonian is like that, the oriented result. And so basically the form of the result is now pretty much identical to what we saw in the DD-DD-OO case, except for various prefactors that come in. Basically we'll have now contribution from weight 1 octopole and also now weight 1 and weight 3. And so we can write down the results immediately for the various geometries considered. And so we have now for the mixed species B, only weight 1 appearing. But for species C, which is pure electric octopole polarizable, there'll be weight 1 and weight 3. And so again, we'll see higher order corrections to the triple dipole appearing. Similarly then for the collinear geometry, and I can sort of get the idea now. So we've looked at a lot of potentials involving electric octopole coupling, starting with the triple dipole case, and saw then that we get sort of interesting features that emerge when we include that particular interaction term. You see that it's advantageous to employ this Hamiltonian, which is then quadratic in the electric displacement field, reduces the work and allows us to calculate these potentials really easily. And we found these higher order corrections, as I mentioned, and interestingly, for mixed dipole octopole polarizability, the contributions from weight 1 only survive with weight 3 vanishing. So with that, I'll end, and thank you for your attention. Be happy to answer any questions.
Thanks very much, Akbar. Yeah, so do we have any questions? Yeah, Paolo.
Wait for the
microphone, please.
Okay. Thanks. Is there any specific reason why you didn't talk about quadrupole? You jumped from dipole to octopole.
That's right. So I said the quadrupole results are all there in those 2 papers that I mentioned. I'll say that there isn't anything especially interesting. The results that I've shown you for the Octopole case have been obtained for the Octopole as well. But basically, if you look at the form of the interaction of the Octopole with the field, so Qij grad J di, basically the Octopole moment that's contributing is basically a wave 2. The scalar zero weight contribution vanishes. So basically it's the symmetric traceless Octopole moment that contributes. So you don't get any higher order corrections to the dipole case in that particular multiple moment contributing. That sort of.
Okay.
How does this compare with contributions from purely dipole terms in higher order of perturbation theory?
Yeah, so clearly the Casimir boulder is the leading one. 2 particles, 2 bodies, dipole polarizable. One should probably go next then to dipole quadrupole 2-body, dipole octopole 2-body, maybe electric dipole, magnetic dipole 2-body. 3-body terms are now going to be smaller, but for some systems, those ones I mentioned and others, it is important now to include those 3-body terms, triple dipole at least. But now people are beginning to want more accurate potentials and are looking at now higher multiple contributions to many body terms, especially for those sort of collisions at ultra cold temperatures.
Actually, I have the same question, so I will reiterate it. So instead of going to higher terms of the multiple expansion, you can go to higher terms in the perturbation theory. So while having dipole-dipole coupling, you can go to having 3-body contribution, but in 4th order of the perturbation theory. So you will have then an integral which would involve a product of dynamic polarizability of A, dynamic polarizability of B, and dynamic hyperpolarizability of C. And I guess that's what you mean.
Okay, that's right. So even in the 2-body case, there's a higher order correction, a 6th order of perturbation theory between 2 hyperpolarizable molecules, beta, for example.
And for the 3-body, is it known, the form of this higher order?
Not that I know of. I haven't seen anything in the literature. But also, nobody really has looked at, I don't know of a result in the literature where the interaction between 2 hyperpolarizable molecules is known for all R. I know the asymptotic limits, I know the short range, R to minus 9, I know the long range, R to minus 10, but nobody has calculated. So that's an interesting problem. I did try it many years ago. It's not easy. So to look at now 3-body alpha, alpha, beta, if you want to call it, yes.
Okay, I think Rudy.
Thank you. If I'm not mistaken, you always look at the angular average, is that correct?
Yes, I showed you results for the oriented case, so for 3 atoms or molecules
Is
that
there
fits.
anything of interest there? Let's say non-pairwise additive orientationally.
They will be important, so for example, in the solid state in crystals, for example, then you can use that oriented results, for example, for noble gas crystallization energies. That's when you would use those, that's right. But you don't, those answers are very lengthy, because you've got to have all the possible direction cosines coming in. Sure.
That's why I'm asking whether there's anything that you could particularly point out.
Not really. One gets a general distance dependence, whatever, A cubed, B cubed, C cubed, for example, in the leading case.
Okay.
Yeah.
Okay, I think we've got 2 more questions from it. Yeah, over there.
Touching at the last question, have you looked maybe numerically at specific geometric configurations that would favor maximum repulsion or attraction?
No, I just left the results in these general forms and just looked at them, the overall sign of the potential, as I was showing in the triple dipole case. We're just going from equilateral triangle to collinear, changes the sign, and so basically, maybe you can look at other geometries, sure, and other systems. I haven't done that, no.
Okay, I think last question is Ify at the back there.
So I'm trying to understand when is the octopole important. I mean, so I guess, as far, from what I know, I mean, if you're in long enough distances, you care only about the dipole moment, right? Now we talked about retarded. That this octopole thing is only retarded contribution. Retarded is larger than lambda, I guess. Lambda is by far larger than the size of the molecule, so we don't. I would assume you don't care about anything apart from the dipole moment. So as long as you have a dipole moment, and I think you assumed it. Why is it important, and when is it important? Is kind of my question. In which distances?
That's a fair point. I mean, as soon as one goes beyond the actual dipole approximation, how important are those higher multipoles? And then obviously 3 bodies, even weaker, as we saw, these potentials are falling off very, very quickly. And for most work, it's good enough to use just the London approximation. But there may be specific. So helium dimer was one fairly, not too far back example where one had to go to dipole, quadrupole, and octopole for the 2 body potentials to get an accurate curve. Because the wave function extends out very far, the potential is very shallow. There may be other molecules where then octopole, but yes, I think that's fair. That it's not.
But I mean, if you go to really short distances, much shorter than the wavelength, then I assume maybe the internal structure of the molecule embedded in multiples higher than the dipole, then it's important.
That's right. So if the size of the chromophore is large relative to then the variations of the field that experiences, that's right, then those higher multiples can come into play. Sure. And then obviously spectroscopic selection rules symmetry of the species as well.
So, a related question. So basically, you could observe a correction of this octopole term by considering large molecules. So with a larger dimension, you should observe this type of correction well with respect to the electric dipole contribution.
In theory, yes.
The pure electric contribution.
I've done that experimentally, because I mean even the molecule dipole hasn't been observed, although I stand corrected.
Yeah, because there was a work of Stefan Schill about for electric quadrupole molecules also. And it shows this type of correction, if I remember correctly, but I don't know.
Okay.
Very good.
Okay, so let's thank both speakers for the session again. And we will then reconvene after a short coffee break at 10:35, so you've got 15 minutes.